So let's look at a situation, which hopefully we'll all start seeing here in a couple weeks. We have a man throwing a football. Now, most of us have thrown footballs or baseballs or something, or at least we've at least seen it done, and so you probably have a good idea of what's going to happen to this football after he throws it. It's going to take a particular path, which will look something like that. The ball goes up, the ball comes down. While it's doing that, though, the ball moves to the right in this case. So we have motion that's occurring in two dimensions. We have an up and down component, and we have a side-to-side component. What is handy about characterizing things like velocities and accelerations as vectors is that we know we can always take a vector apart. We can decompose it into components that lie along our coordinate axes. When I do that, what I'm actually doing is I'm enabling myself to analyze the motion of this ball, which is somewhat complex, simply as two one-dimensional systems. So instead of trying to analyze the motion of the ball in a combination of x, y, I'm going to analyze it in y, and I'm going to analyze it in x separately. I can always put them back together later if I want to. We learned how to take vectors apart. We learned how to put them together. I can do the same thing here. Okay, so let's look at the motion. What is happening in the up-down direction? So let's up-down. Well, hopefully we know that this ball is going to be under the influence of gravity, and so it's going to experience the acceleration due to gravity, which is always in the up-down direction, right? Well, specifically, it's always down, a little g. So I can say that the acceleration in this direction, which why not? Let's call it y, is equal to minus g. What I've done is let's just explicitly say my positive directions are up and to the right. You can always change those later, but if that's the case, then I get the acceleration in the y direction is minus g. All right, so left-right direction, which we normally call x. What is happening in the x direction? Well, it's a little bit hard to see if we don't know about forces yet, which if you're in my class, we haven't talked about forces quite yet. But if you really think about it, there's really not much happening in the left-right direction apart from the ball moving. Remember, we're always going to ignore air resistance, at least for now in this class. We're going to ignore air resistance. And so there's nothing acting on the ball that could slow it down or speed it up. Once it's left the hand of the quarterback, nothing is influencing it except for gravity. And gravity's up-down. And the left-right, there's actually nothing that could speed the ball up or slow it down or even change its direction. And so in the x direction, what we find is that the acceleration is 0. So in the y direction, I'm in free fall. In the x direction, I'm in equilibrium. That actually makes things pretty easy to handle. Now, once I have this, I can start to talk about other things like the velocity. So let's draw the picture of the velocity of this ball. I'm going to draw a vector at the start of that motion that looks something like this. Now, if you've ever thrown something, you kind of know what that means. I can define this as an angle theta. Notice that this vector is tangent to the path. We've talked about that a little bit, but let me remind you what a tangent line is. A tangent line is a line that intersects a curve. A tangent to a curve, I should say, intersects the curve at exactly one point. I could draw this vector intersecting that curve at several points. I could draw it intersecting the curve at no points. There's only one way at every point I can draw a line intersecting the curve at exactly one point. That's the tangent line, and that turns out to be what the velocity at every point looks like. Here, I've drawn it tangent to the start of the motion. Okay, let's call this V0. And this theta, if you've ever thrown something, you know what that is. You can throw it at a steep angle, you can throw it at a shallow angle. You can try to throw it straight, you can try to throw it up, or you can throw it in some sort of combination of those. And how far you want it to go depends, you pick that angle depending on how far you want it to go. So I'm going to call this V0. Just V0 is a handy way to handle it. We'll put in initials and finals as we line that up with our equations. But for now, let's just call this V naught. And as soon as I draw it like this, you probably see where I can go with that. I can decompose that V naught into its component vectors. I can talk about V naught x and V naught y. There's V naught x. There's V naught y. Okay? Well, in the up-down direction, it looks like V initial, my initial velocity, turns out to be V naught y, right? What is V naught y? It is V naught sine theta. We know how to decompose that vector. And in the x direction, I should be careful here. V initial y, I'm going to have to subscript for the bookkeeping. V initial x turns out to be V naught cosine theta, the x component. So now, interestingly enough, I have y components of the acceleration, y components of the initial velocity. I have x components of the acceleration, x components of the initial velocity. And you can see what I'm doing. I'm building up a system of things that I'm going to be able to use to analyze this motion using kinematic equations. Okay. So in the next video, we're going to look at a couple of special cases, how the position of this gives us different velocities.